Our next example from the book is problem 10.45. It's on page 455, 10.45. And it's kind of similar to the last one, but I like it. And also I should tell you there's a typo in the book. So anyway, here it goes. In a 1907 study of 16 steamships ranging in tonnage from 192 up to 3,246 tons, and in crew size from 5 to 32 men, the following results occur when crew size is regressed on tonnage. Alright, so crew size regressed on tonnage. Crew size is the dependent variable, and tonnage is the independent variable. Now why did they choose it that way? Could they have just switched the order of these variables, put tonnage up here and crew size there? Yes, they could. And would it change things? Cosmetically so. But probably this is a more natural way, because think of, this axis is our independent axis, our input axis. And so if you're around 1907 and you build a ship with a tonnage of 2,000, then you could use this analysis to predict the crew size you would use. Okay, you would be less likely to go backwards and say, well, look, I can afford a crew size of 24. What size boat can I get? You could think that way, but probably more likely, based on this size boat, how much crew would be normal to man this boat. So, tonnage, did I spell that right? Yeah, 2 N's. It's got 2 N's. That's not a word I spell a lot. So, tonnage, incidentally, is the amount of weight a boat can support. And it's not clear to me if that's the size of the entire boat or how much can be loaded into its cargo. I think it's probably the entire boat. But sometimes it's called displacement. And you could figure out how much, based upon the tonnage, you could figure out how much the boat is in the water based upon how much water weighs that amount in tons. Anyway. So let's write out the equation here. Crew size, in other words, the number of people it takes to run a boat, is 9.5 plus 0. Let's see, there's 2 zeros, 0062. So please fix that. Your book has an extra 0 here. In order to make things work out, this needs to be 0.2062, not 3 zeros. So that was a typo in the book. All right. So there's the equation, the regression line equation, and they said that. And by the way, what does it look like? Well, for a boat with no tonnage, they expect a crew of 9.5 guys to run it. And then over here, this was what? The highest they had was 3,246 tons. And highest crew size went up to 32. Now I don't know if that particular ship had 32 guys on it. But anyway, it's regression line looks like this. Now the data I would expect is probably it's scattered. It's scattered in there. And what's interesting is that the y-intercept is 9.5, but the least amount of crew members it took for one of these ships was actually only 5 people. And so it took 5 guys to run a very small ship. I think there's an explanation for that, but I'll get into that in a bit. Okay, so we have some analysis variables here. The correlation coefficient was 0.87. That's a strong positive correlation. And the t-score was 6.79. I would probably put t-star. The calculated t-score is what I use a star for. degrees of freedom was 14, which tells us that N was 16. In other words, there were 16 samples. Well, they told us this. It was a study of 16 steamships, and degrees of freedom in regression analysis, linear regression analysis, is 2 less than sample size, N minus 2. And then when they did the hypothesis test, they had a very, very small p-value. So, part A, what do the numbers tell you about the relationship between the two variables? Well, I'm looking at this and I'm saying there's a strong positive correlation. And let's go ahead and do r squared. R squared would be, what would that be? Oh, 7,569, I think, is 87 squared. Let's see, 0.87 squared is 7056. Oops, I didn't calculate that very well mentally. Oh, no, I put the wrong number in. 0.87 squared is 7569, yeah. So that rounds off to 76. Let me suggest, if you want to score points with me, in this kind of analysis, look at r squared also. Calculate r squared. Because r squared is an important number, important piece of information. It tells us, in this case, that 76% of this data is explained by the relationship between tonnage and crew. 76% depends upon that relationship between the size of the ship and tonnage and the number of crew members it takes to run the ship. The other 24% is due to other residual variables, other issues. You know, it could be the machinery it takes to run a boat, and all kinds of factors there. Maybe the experience of the crew. So, what do the numbers tell you about the relationship? Well, strong positive correlation. 76% of the data is explained by the relationship between tonnage and crew. It's a significant positive correlation because the hypothesis test showed that the p-value was extremely small. So it's less than 1 chance in 10,000 that this is due to just random chance. And so it's a good analysis that way. 16 pairs of data. So about what we know about this data. Part B, on the average, how large is the difference in crew size for 2 ships that differ in tonnage by 1,000 tons? Okay, so if the difference is 1,000 tons, if I multiply my slope, 0.00, oops, 2 zeros, 0.0062 times 1,000 is 6.2. And so that tells us that the difference between 2 ships that are different in terms of 1,000 tons is 6.2 crew members. So we expect that it requires a little over 6 crew members to run the larger ship. And there you go. That's the rate of increase is for every extra ton, we require 0.0062 crew members. Well, for 1,000 tons, that would be 6.2 crew members. Part C, what is the estimated number of crew members for the smallest ship, and what is the estimated number of crew members for the largest ship? Right, well, for the smallest ship was 192 tons. Apparently that's pretty small. So if I plug in 192 here, I've got 9.5 plus 0.0062 times 192 tons is 10.7 crew members. So we expect 10.7 crew members for that smallest ship. Okay. Now apparently one guy was able to run a ship with 5 people. So 10.7 seems high according to this analysis. And what is the estimated number of crew members for the largest ship? Well, the largest ship was this number, 3246. So if I plug this number into tonnage. Instead, I get 3246, 29.6. So it was 10.7 versus 29.6. So for that larger ship, we expect almost 30 crew members. And apparently the largest ship had 32 crew members, so a little higher than you might expect. I think the reason why this was a bit off down here, because the lowest ship was 5. In actuality, it had 5 people. Seemed like I had an possible explanation for that. Yeah, maybe I don't. You know, there are key positions on the ship. They have to be manned. You have to have, you have to have a captain. You have to have some guy to do this, another guy to do that, and it seems like there's always a minimum, regardless of the size of the ship. And that, but this sort of contradicts it, because one ship was run with 5 people. So I guess I don't have a good explanation for that. I thought I had. All right, well, that's about what I have to say about this problem. And again, you want to think about what slope, what does the slope of the regression line tell you? What does the regression line itself tell you? It allows us to make projections based upon input. We can project an output, kind of an average projection. So there's that problem.